One of the first things you're going to have to do when you go to run your sample is you're going to have to choose an instrument geometry. And so the two main geometries that we have are Bragg-Brentano, or BB, and parallel beam, or PB. Now, these are the two main geometries. We do have other geometries available, and if you think that your sample may require one of those other geometries, please contact me and we can discuss it. But for the purposes of today's training, I'm going to restrict our discussion to the most common types of geometries. Now, in Bragg-Brentano geometry, if we look at this diagram down here, we see that the X-rays are generated at this X-ray generator. They diverge as they travel towards your sample. The sample acts as a mirror and refocuses those X-rays at the detector. This geometry is really good for powder samples. If you do have powders, let me know. I have a short video I can send you of how to prepare your powder samples in a holder. But in general, it's good for flat samples because if you have a sample that is not flat, you're going to get some errors in that measurement. And the Bragg-Brentano geometry is especially prone to those types of errors. So flat samples on the order of, a micron or so flat is something that's going to work well for Bragg-Brentano. If your sample is really rough, on the order of hundreds of microns, then maybe Bragg-Brentano is not the best geometry for you. Bragg-Brentano is also good for thick films, and it's going to give you more signal and better resolution than other geometries. So if you can use it, you should. Now, some samples are rough, or you have thin films, or you have a sample that might change height, for example, if you heat it. And in those cases, you're going to want to look at parallel beam geometry instead of Bragg-Brentano. Now, the one main difference between these geometries is that the X-rays are going to hit a mirror on their way to the sample, and that mirror is going to act to collimate the X-ray beam so that you have a parallel beam of X-rays traveling towards the sample. In addition, there are some optics that we have to change out, but the software will guide you through that process. So once you've made this kind of determination, then you may also want to think about the type of sample that you have and how you want the source and the detector to move. So in all of these schematics, I assume that the source is on the left and the detector is on the right. That is exactly what you're going to see when you are in front of the instrument as well. And so the most common geometry for doing experiments is a theta to theta geometry. And in that experiment, the source and the detector move at the same time and at the same rate. And so the source will start at a low angle and move to a higher angle, and the same thing will happen with the detector. So we call this a symmetric experiment. The source and the detector move at the same rate. But one important thing is that in this experiment, we only measure planes that are parallel to the surface of the sample. So that's where this diffraction vector comes into play. This diffraction vector indicates what direction the planes are in that we're measuring. And it's always perpendicular to the planes. So in this case, we would be measuring planes in this direction. Sorry, my drawing is not very good with a mouse. So planes that are parallel to the surface of the sample are the ones that we're going to be probing in this type of theta to theta geometry. Now, if your sample is ideal and it's randomly oriented crystallites, then it doesn't really matter. We're going to measure every single spacing in your sample because you're going to have sample crystallites that are oriented in every possible orientation. So even though we're only measuring in this one direction, you are going to have crystallites oriented so that you can measure every single spacing in your sample. If your sample has some kind of preferred orientation, then you may need to think about this a little bit more carefully because you are only going to be measuring these types of planes, and you may not observe other planes that are oriented in different orientations at all. And so keep that in mind. Now, on the right-hand side, I wanted to show a grazing angle geometry, because I know a lot of you are going to have thin films where you may want to confine the beam to a thin region on the surface. In that case, we do what's called a theta scan. So here we're going to fix this source at a low angle, and we're not going to move it. We are only going to move the detector over here on the right. Now, when we do this, this is called an asymmetric experiment, and you'll notice that this diffraction vector is moving. That means the orientation of the planes that we are probing changes during the course of the experiment, which is different than what we saw with this theta to theta geometry, where this diffraction vector was constant. I hope I've given you a little bit of an introduction to X-ray diffraction and some of the decisions you're going to have to make when preparing to take data. Again, if you have questions about anything covered in this background information, please make sure to note them and ask them to me when we meet live.